Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 1, and today we're going to have a discussion about decimal numbers. This should hopefully be a review topic for anyone that's graduated kindergarten. So, 10 digits, 10 fingers. Coincidence? I think not. So, as easy as this topic may be, trust me, where you're not wasting your time because this is a valid technique to learn binary number, which is how computers count. So we're going to review decimal numbers and we're going to take the topics that we learned today and bring it right into binary numbers. Okay, so decimal numbers. Everybody knows you've got the numbers 0 through 9. And those are the only numbers we use. But we're not limited to 9. If you want to go to count above and beyond 9, we use a combination of 2 or more digits where the position is indicative of weight. And that's a critical concept. So position is indicative of weight. So 0, 1, 2, counting up 7, 8, 9. What do we go to? 1, 0. We're adding a number to the left of it in this particular case, i.e. it's a new position and it's indicative of a weight, a higher power. Well, what does it represent in decimal? It represents powers of 10. So every time we move to the left, we move up a power of 10. And what are powers of 10? So let's say 10 to the 0, 10 to the 1, 10 to the 2, very similar to our counting, 0, 1, 2, 3, all the way up to 9. We're just increasing them in this direction, 10 to the 3, so on and so forth. What do these represent? Well, 10 to the 0, if we remember right, anything to the 0 power from electronics 2, or excuse me, electronics 1, you should remember this. Anything to the 0 power is 1. Well, same thing in this course, it's still a 1. 10 to the 1 is a 10. 10 to the 2 is 100. 10 to the 3 is 1,000, and so on and so forth. Basically, in our decimal system, we're using powers of 10. And the whole number represented in a decimal, it's basically the weight in powers of 10 multiplied, the digits. Let's just do an example. So 42. What is 42? Well, it's the 2's in the 10 to the 0 spot. 4's in the 10 to 1 spot. It's basically the sum of the digits when each digit has been multiplied by its appropriate positional weight. So 2 times 10 to the 0 plus 4 times 10 to the 1. So 4 times 10 plus 2 times 1. 40 plus 2. 42. No big surprise there. So basically, the sum of the digits where each digit has been multiplied by its positional weight. That's how the decimal system works. That's how the binary system works, which you'll see in a little bit. Okay, so another example of a decimal number, 1, 2, 3.4. It's got this decimal in it. So, decimal point, excuse me. How do we figure that into our equation? Well, if this was increasing powers of 10, at the decimal, what happens? It's decreasing powers of 10. So, for our 3, it's 3 times 10 to the 0 plus 2 times 10 to the 1, because that's in the 10 to the 1 spot, 10 to the 0 spot, 10 to the 2 spot. So 1 times 10 to the 2. What is this? Well, it's decreasing powers of 10. If the decimal was to the left here is 10 to the 0, what's a decreasing power of 10 is 10 to the negative 1 plus 4 times 10 to the negative 1. So 1 times 100 plus 2 times 10 plus 3 times 1 plus 4 times 0.1, 100 plus 20 plus 3 plus 0.4 gives you 123.4. So it makes sense. The sum of the digits when each digit has been multiplied by its appropriate positional weight. So let's go ahead and just do a couple examples. What is the positional weight of the 6 in these two numbers? Well, look at their position. They're obviously different values. They're not just equal to 6. That wouldn't make sense. Why would 360 be different than that other number, 61,209? So 360 is 3 times 10 to the 2 plus 6 times 10 to the 1 plus 0 times 10 to the 0. 3 times 100 plus 6. Oops. Getting ahead of myself here. Plus 6 times 10 plus 0 times 1. 300 plus 60 plus 0. So the value of that certain position, it's got a 60 as opposed to just a regular 6. And by extension, what's this guy right here? So 6, 1, 2, 0, 9. What's the positional weights? 10, 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. So it sounds like it's 6 times 10 to the 4. So that would be 6 times 10,000, which would be 60,000. Makes sense. It's 61,000. And that 6 holds a value of 60,000. Okay, it's not just equal to 6 because it's in a different position, has a whole different value. So let's see, just see a couple more examples here if you can do this. Break 56 down and put it in the same format. Let's just make it even a little bit harder. Break 56.1 down in the decimal system and put it back together in the same method we've done up here. And let's do 4.67. Let's do those two numbers. So, okay, let's do 56.1. 56.1. That's 10 to the 0. That's 10 to the 1. It's 10 to the negative 1. 5 times 10 to the 1 plus 6 times 10 to the 0 plus, what is it, 1 times 10 to the negative 1. 5 times 10 plus 6 times 1 plus 1 times 0.1. 50 plus 6 plus 0.1. 56.1. Okay? 4.67. Where's our decimal place? Right here. That's the 10 to the 0 spot. That's 10 to the negative 1. That's 10 to the negative 2. So 4 times 10 to the 0 plus 6 times 10 to the negative 1 plus 7 times 10 to the negative 2. 4 plus 6. Whoops. I should do this all in one step. Times, excuse me, in a number of steps. 7 times 10.01. 4 plus 0.6 plus 0.07. And if someone came up to you on a street and just gave you this as a math problem, your answer would be 4.67. Makes perfect sense. Okay? So as easy as this concept may be, where position is indicative of weight, and to the left of the decimal point represents increasing powers, and to the right represents decreasing powers, and our synthesis of this, where the sum of the digits, when each digit has been multiplied by its positional weight, these are all very useful discussions to have as we go into the discussion of binary numbers, which is going to be our next lecture.